This paper explores the advantages of representing and processing semantic knowledge extracted into graphs within the emerging paradigm of semantic communications. The proposed approach leverages semantic and pragmatic aspects, incorporating recent advances on large language models, LLMs, to achieve compact representations of knowledge to be processed and exchanged between intelligent agents. The approach uses a cascade of LLMs and graph neural networks, GNNs, as semantic encoders, where information to be shared is selected to be meaningful at the receiver. The embedding vectors produced by the proposed semantic encoder represent information in the form of triplets: nodes, semantic concepts, entities; edges, relations between concepts, and nodes. This representation associates semantic information with the relationships among elements in the space of semantic concept abstractions. The paper investigates the potential of achieving high compression rates in communication by incorporating relations that link elements within graph embeddings. The authors propose sending semantic symbols solely equivalent to node embeddings through the wireless channel and inferring the complete knowledge graph at the receiver. Numerical simulations illustrate the effectiveness of leveraging knowledge graphs to semantically compress and transmit information. The paper identifies three key pillars for semantic communications: pragmatic goal-oriented communications, optimizing compression of knowledge representation, and sharing and updating a mutual knowledge base between transmitters and receivers. The authors focus on graph-based pragmatic semantic communications, where information extracted from data is semantically represented in knowledge graphs formed by nodes, entities, and edges, relationships. The knowledge graphs provide structured representations of knowledge, organized into triples in the form of node relationship node, enabling the incorporation of semantic meaning into data. The authors aim to develop a new AI-native semantic architecture where the semantic plane, semantic RAN intelligent controllers, SRIC, and semantic reasoning engine units are defined, enabling new knowledge-centric applications. The paper highlights the importance of considering the context and goals of communication in optimizing the compression of knowledge representation. The authors propose using metrics such as age of information, AOI, and value of information, VOI, to evaluate the repercussions of semantic incongruences on the efficacy of decision-making processes. Overall, the paper presents a novel approach to semantic communications, leveraging graph-based knowledge representation and LLMs to achieve compact and meaningful representations of knowledge. The proposed approach has the potential to enhance the efficiency of distilling data for transmission and improve the resilience against noise of the communication process. Limitations and future work include investigating the scalability of the proposed approach, exploring different types of knowledge graphs, and developing metrics to evaluate the performance of semantic communication systems. In semantic communication systems, knowledge graphs are used to represent semantic symbols as node relationship node triples for extraction and interpretation. Recent approaches focus on enhancing accuracy, reducing interpretation ambiguities, improving data compression efficacy, and increasing error correction robustness. However, these approaches neglect the embedded meaning in the semantic message captured in the graph structure. This paper proposes a novel end-to-end pragmatic optimization semantic communication framework, optimizing the transmitter, latent space representation, and receiver. The framework represents semantic messages as pragmatically sparsified knowledge graphs relevant to the receiver given the locally available knowledge. To learn the semantic relevant knowledge graph representation in lower dimensional latent spaces, a pre-trained large language model, LLM, module is cascaded with a graph neural network, GNN, module. The LLM module associates embeddings with source data, while the GNN module processes the combined output with the available inherent graph topologies of the data. The proposed semantic architecture encodes the knowledge graph in a batch of vectors, each containing semantic information about a node, its connected nodes, and the relations between them. The system model consists of a knowledge graph G equals N, E, where N represents the set of nodes and E represents the relational structure amongst these nodes. Two semantic encoders are proposed: enclum, GNN, and enclum, FFN. Enclum, GNN cascades a pre-trained LLM with a GNN, synthesizing node representations by fusing textual and relational information. The GNN generates a compact representation vector of the node by fusing the initial features of the neighboring nodes and the initial features of the relations, as given by equation 2. The second proposed encoder, enclem, FFN, is composed of a cascade of a LLM with a feed-forward neural network, FFN, bottleneck, performing compression of the initial feature vector associated with each node without considering the associative relationships in the knowledge graph, as given by equation 3. The proposed framework numerically illustrates enhancements in both compression rates and communication robustness, providing a novel approach to semantic communication systems. The system model of semantic representation learning on graphs is illustrated in Figure 1. A large language model, LLM, associates the initial feature vector xi with the node descriptor ni, which is then compressed by a feedforward network, FFN, via a tunable bottleneck layer. The channel encoder, comprising an FFN and a power normalization layer, modulates each low-dimensional vector z from the semantic encoder into k-complex symbols. These symbols are then demodulated by the channel decoder, using an FFN architecture, back into the set of latent space vectors y equals, y, ni equals 1. To determine the optimal channel encoding function for an additive white Gaussian noise, a WGN, channel, mutual information is employed, approximated using the Mutual Information Neural Estimation, MINE, framework. The semantic decoder receives the message G and decodes it from a set of embedding vectors y equals, y, ni equals 1 to infer a knowledge graph congruent with the one intended by the source. The decoder combines two decoding functions, a node classifier and a relation classifier. The node classifier, modeled after a multi-layered perceptron, MLP, with skip connections, categorizes n distinct decoded embedding vectors, attributing each to a specific node. The relation classifier reconstructs the edges within the knowledge graph by utilizing node representations obtained from the graph encoder, processing combinations of embeddings to associate commensurate relations. The system is trained using a loss function that includes a cross-entropy term augmented with a penalty parameter considering a weighted mutual information component. The trainable parameters of the semantic encoder and the semantic decoder are theta and th, respectively. The loss function reflects the interdependence between variables x and y across the semantic channel from transmission to reception. By minimizing the loss function, the system aims to learn a compact and informative representation of the knowledge graph, capturing the relationships between nodes and edges. A novel framework for graph-based end-to-end wireless semantic communication systems is presented, focusing on node inference and relation establishment. The loss function LCE is minimized as the sum of two components, LCEG, representing node inference loss, and LCER, representing relation loss. Each training epoch consists of two steps. First, calibrating the mutual information estimation model, and second, training the end-to-end model using a dual objective optimization strategy that combines cross-entropy loss minimization with mutual information maximization to improve predictive accuracy. Numerical results assess the performance of the proposed framework, comparing two encoder designs, enclem, GNN and enclem, FFN. Evaluation metrics include node classification accuracy and F1 score, measuring the average equivalence of nodes and relations between transmitted and decoded knowledge graphs. Results show that enclem, GNN outperforms enclem, FFN in terms of node classification accuracy for an embedding compression factor of 24 or smaller. In an additive white Gaussian noise channel, the graph-based semantic encoding and decoding approach outperforms traditional techniques in the low signal-to-noise ratio regime, requiring about 14 dB less SNR to reach the maximum F1 score. The semantic approaches also demonstrate a significant compression gain, with an average compression gain factor of 5.54 compared to Huffman encoding and 7.17 compared to 6-bit encoding. The proposed framework's effectiveness is attributed to the inclusion of graph topology information in enclem, GNN and the superior efficacy of graph neural networks in condensing the semantics of graph nodes. The use of a pre-trained language model to produce feature vectors of size 384 is also noted. The framework is evaluated using knowledge graphs from the WebNLG project, with training performed at a reference SNR of 14 decibels and a batch size of 8 graphs separately for both encoder designs. The results demonstrate the potential of the proposed framework for efficient and robust semantic communication over wireless channels. A novel method for semantic encoding and decoding of knowledge graphs is presented, enabling the compression of knowledge representation. Two variants for semantic encoding are introduced: enclem, GNN, which exploits the relational spectrum of nodes, and enclem, FFN, which treats each node isolated without considering its neighborhood. The proposed framework is validated through numerical results, demonstrating the effectiveness of enclem, GNN and enclem, FFN in achieving high node classification accuracy. Notably, enclem, GNN achieves almost 99.5% accuracy, while enclem, FFN reaches 94% accuracy. Furthermore, enclem, GNN enables a compression factor of up to 24 for the node's embedding size while maintaining node classification accuracy almost independent of the compressed embedding size. This is a significant improvement over traditional methods. The graph-based semantic encoding and decoding functions are compared to traditional Huffman and 6 bits coding in the low-average SNR regime. The results show that the proposed design outperforms traditional methods, requiring about 14 dBs less of SNR to reach their maximum F1 score. This highlights the enhancements in both compression rates and communication robustness achieved through the proposed design. The author's approach is based on a deep understanding of knowledge graph representation and the importance of semantic encoding and decoding. The proposed framework has the potential to significantly impact the field of knowledge graph representation and compression. The comprehensive list of experiments and results provided in the paper demonstrates the effectiveness of the proposed method and highlights its potential for real-world applications. The proposed framework has several advantages, including improved compression rates, enhanced communication robustness, and high node classification accuracy. The results demonstrate the effectiveness of the proposed method in achieving high performance in knowledge graph representation and compression. The author's approach has the potential to significantly impact the field of knowledge graph representation and compression, enabling new applications and use cases.